Now we're going to talk a little bit more about issues in virtual memory, but some of which we've already talked about. So these are some extra slides for your benefit. I'm going to go through some of them quickly. But we already discussed how large is the page table and how do we store and access it. I'm going to give you a little bit more example from real systems with some additional slides, but we're going to skip some of the slides. The second question is, how can we speed up translation and access control check? Again, we've discussed this, TLBs. But again, these are very important. That's why I raise up these questions. And then there's a third question, which was brought up by one of you in the last lecture, I think. When do we do the translation in relation to the cache access? And that's going to be important. I'm going to give you a teaser of that, but we're not going to go into the details. There's some backup slides and some lecture references you can take a look at. There are many other issues in virtual memory that we will not cover in detail. I mentioned some of those actually while we were discussing some earlier issues. What happens on a context switch? How can you handle multiple page sizes in an efficient manner, etc. We're going to touch upon some of this when I give you a real world example, but not in great detail. So issue one is, how large is the page table? Where do we store it? In hardware, physical memory, virtual memory? I think we've already discussed these questions. With multi-level page tables, part of the page table is in physical memory, and the rest is in virtual memory, and some of it is not allocated also. And how can we store it efficiently without requiring physical memory that can store all page tables? And the idea is multi-level page tables, as we have discussed, right? And this is the slide that I'm showing you for the fourth time, perhaps, because we have seen it in the last lecture also. And we've already discussed the solution. And we discussed how to do the page table access. There's a page table base register. There's also a page table limit register so that you don't exceed the virtual memory that you're accessing. If virtual page number is out of bounds, it exceeds the page table limit register, then the process did not allocate the virtual page. So there's an access control exception that happens based on that as well. So there's hardware checks. x86 actually has segmentation also, as we discussed in the last lecture, which is a different level of protection, but it's not as important today. That's why we don't talk about it as much. Okay, we already discussed that page table base register is a part of process context. It's an architectural register, and it needs to be loaded when the process context switched in. If you don't do that, then you have a problem, basically. And it's the hardware's job to do that. If you don't do that, actually, the process will be using somebody else's page table base register, and you basically compromise security and privacy right away, right? So the hardware bugs at any level of this process can directly affect your security and privacy, basically. Okay, I've already given you these examples. I'm actually going to skip to the page table entries that are more, so these are more recent. This is x86-64. You can see that page table entries have increased to 64 bits. So they used to be 32 bits over here. Each of these are page table entries. And you can see that now they're 64 bits. Why? Because we need to be able to address larger and larger virtual and physical memories. And so you can see that there are different types of page table entries, CR3. There's possibility of 5-level paging in x86-64. So this is a 5th level, which is they don't call it the directory anymore, of course. This is the 1st level if you have 5th level. This is the 1st level if you have 4 levels. And you can see that there are 1 GB page frames also. So there are 3 types of pages in x86 right now: 1 GB, 2 MB, and 4 kilobytes. And you need to choose which page you want. This is a tough choice, not an easy choice, or the system needs to choose for you what type of page they want. And again, it's a tough choice, basically. It depends on your locality characteristics and your translation, right? And you can see that the other flags also exist. There's nothing special that I want to provide over here, other than this is the 4-level paging example that I showed you earlier, right? We're not going to go through this again, but existing systems are complicated multi-level page tables. This is 4-level paging for 4 kilobyte pages, I should say. This is 4-level paging for 2 megabyte pages. So it's, and this is 4-level paging for 1 gigabyte page. So clearly for 1 gigabyte page, you actually don't have 4 levels, right? You have 2 levels over here. And you have 3 levels for 2 megabyte pages, but this is the 4-level paging is the name of the paging mechanism that they use. That's why it's called all 4-level paging. The maximum levels is 4 with the smallest page size. Okay, so that's how large is the page table and how complicated it gets, basically. So how can we speed up the address translation and check? We already know about translation look-aside buffers. We've already talked about how to make it fast. Let's talk about who manages it, meaning what if you miss in the TLB? So TLB caches the recent access translations, but what if you miss in the TLB? What TLB entry do you replace? Clearly, it's a caching decision. Who handles the TLB miss? Hardware versus software. And there are advantages and disadvantages. In many systems today, hardware is increasingly handling the TLB misses, but there are actually some systems that handle the page TLB misses in software, like MIPS actually handles TLB misses in software. And that gives more flexibility to the system. And we're going to talk about the trade-offs. And then what should be done on a page fault is, what if you actually find out the PTE eventually and figure out that it's a page fault? Then what virtual page do you replace from physical memory? These are different events. I want to emphasize that TLB miss is very different from page fault. TLB miss is that says that the translation is not cached in the TLB, in the hardware TLB. Page fault means that the physical page corresponding to this virtual page is not mapped in physical memory. It doesn't exist in physical memory. So you need to bring it. You may get a TLB miss that doesn't result in a page fault, obviously, right? You can actually have a valid page table entry. You may get a page fault that doesn't result in a TLB miss. That also happens if the page table entry is cached in the TLB, but it becomes invalid for some reason. And there are reasons for it, for TLB coherence reasons, for example. When you, for example, replace the page that is subject to the translation, you may actually invalidate that TLB entry. It depends on how you invalidate exactly the TLB entry, of course. But this is certainly possible also, depending on how you implement things. But it's more rare, of course. So who handles the page fault? It's usually the software, basically. Hardware can potentially accelerate it. But so actually, I should say it's cooperative, but it's done under the supervision of the software, basically. You usually have an exception that leads you to a software handler, and the software handler decides what to replace and how to handle the page fault. Usually, hardware handles the TLB, but not always. Okay, we already discussed the TLB. This is a more generic explanation, so you can take a look at it. But basically, the TLB is small. It cannot hold all PTs. Some translation requests will inevitably miss in the TLB. So you must access memory to find the required PTE. This is called walking the page table. Essentially, you walk all levels of the page table in a multi-level page table to get to the PTE, page table entry you're looking for. And this takes a long time, as you know, right? There's a large performance penalty. So better TLB management and prefetching can reduce TLB misses, just like better cache management and prefetching. But then eventually you get a TLB miss. Who handles that TLB miss? Is it the job of the hardware or software? Meaning, whenever you get a TLB miss, do you take an exception, or does the hardware handle it? So there are multiple approaches. It's hardware managed in most systems today, x86, ARM, etc., for example. And hardware does the page fault. Essentially, it walks through all of the page table accesses, and it fetches the PTE in the end and inserts it into the TLB. If the TLB is full, the entry replaces another entry. It's basically, you do the replacement. And it's done transparently to the system software. This way, you can employ specialized structures and caches, for example, page walkers and page walk caches that we will see in an example soon. Approach 2 is software managed. MIPS, actually, the architecture that you are implementing, does it, except you're not implementing the virtual memory part. The hardware raises an exception, and the operating system does the page walk using some instructions. You can clearly do that, right? You can clearly construct instructions to access page tables, and the operating system fetches the PTE, and the operating system inserts and evicts entries in the TLB. Essentially, this is software managed TLB. And clearly, there are trade-offs to this approaches, and you can imagine some of the trade-offs. Hardware managed TLBs, there's no exception on TLB miss. Instruction just stalls. Other instructions may already be going on in an out-of-order machine. That's great. Independent instructions may continue. And there are no extra instructions, data brought into caches. You don't do a context switch to a software. So that's the big advantage. And that's why hardware managed TLBs are commonly used today. But then the downside is page directory and table organization is etched into the system. The hardware needs to implement that. And if you change it somehow in software, your hardware that manages the TLB is useless now. So OS has little flexibility in deciding the TLB organization and page table and directory organization. Software managed TLB, of course, doesn't have that disadvantage. The OS can define the page table organization independently of the hardware. And it can also employ more sophisticated TLB replacement policies. The downside is performance overhead. You need to generate an exception, and you need to flush the pipeline, execute the exception handler, and extra instructions are brought into the cache. Of course, you could handle this in another thread. So you may actually eliminate some of the performance overhead, like the pipeline flush, but still there's overhead in executing other instructions to actually handle the software managed TLB. In hardware, if you handle it, you can have a specialized structure completely, as we will see in Intel systems soon. Okay, the final issue that I'm going to briefly touch on is, when do we do the address translation in relation to cache access? And this becomes important, especially from the perspective of the L1 cache. Because if you need to do the translation to access the cache, now translation is on your critical path, right? Critical path of cache access. So this is a teaser. When do we do the address translation? Do you do it before or after accessing the L1 cache? And in other words, is the cache virtually addressed or physically addressed? And this is a fundamental choice at the L1 level, but you could also potentially move it to the L2, L3 levels, but it doesn't make sense fully at some point. And then the difficult question is, what are the issues with a virtually addressed cache? And there are issues. And one issue is synonym problem. Basically, two different virtual addresses from the same process or different processes can map to the same physical address, which means that same physical address can be present in multiple locations in the cache if you're actually using virtual addresses to address the cache. And this can lead to inconsistency in data because the same physical address in different multiple locations, let's say different sets, different indices in the cache. And if one of them is updated, the other one needs to be updated also or invalidated. So you have a coherence or consistency problem inside your own cache if your cache is virtual, because two different virtual addresses can map to the same physical address. There are other problems, actually. This is one problem. There's also a homonym problem, which is the fact that same virtual address can map to two different physical addresses. Why does this happen? Because virtual address can be in different processes, right? Different processes have the same have the virtual address space to each of them, and the same virtual address can be mapped to different physical addresses. And this becomes a problem when you're managing the cache if it's completely virtual. So usually the solution to fix the homonym problem is to introduce address space IDs to distinguish between different processes and address spaces. This is easier to solve at hardware cost. Synonym problem is different virtual addresses can map to the same physical address. And again, why? Different pages can share the same physical frame within or across processes, right? Essentially, different virtual addresses can map to the same physical address. Just like we saw in the Google example, right? Different virtual addresses map to the same file, which is mapped to the physical memory. And many different virtual addresses can map to the same physical address. And there could be many reasons. Shared libraries, shared data, copy and write pages within the same process, files that are mapped. That's part of shared data, actually. And then the question is, do homonyms and synonyms create problems when we have a cache? And is the cache virtually or physically addressed? Becomes a very relevant question over here. And there are ways of solving the synonym problems also. I'm not going to go into detail. I have some backup slides for this, but I would like you to think about it if you're interested in this. So there are three ways of designing the first level cache. It could be physical, meaning it can the access of the cache happens after the virtual to physical address translation. You don't have the homonym and synonym problems, but you have a huge latency overhead. You need to access the cache, you need to go through TLB. And we discussed that first level cache is very latency sensitive. So you don't want to do that. In general, this is not done. The second option is you access the cache completely with virtual address and then do the translation. This is completely virtual, so there's too much flexibility and there's too many homonym and synonym problems because of this. As a result, this is also not done in general. Usually you do a compromise that looks like this, a virtual physical cache or virtually indexed, physically tagged cache, where you access the cache concurrently with the TLB, and then you do the tag check using the physical address. Now, for this to work, you need to design your cache carefully such that the indices, the virtual index, doesn't change during translation. So you should really not index the cache using part of the address that's going to change using the translation. Otherwise, you may actually map two different virtual addresses, two different virtual addresses that map to the same physical location to different locations in the cache. So if you didn't understand that, that's okay. But if you understood it, that's good, because that means that you've actually been really following what's going on in virtual memory. But think about what happens in this case. What kind of bits should you use for the index into the cache? And what can you do and what can you not do? So the idea is virtually index the cache, but do the tag comparison in the cache using physical addresses, because you will have the physical address at the end over here. Okay, and usually systems employ this sort of caches. Virtually indexed physically tagged cache at the first level. The problem is not present in the lower level of the hierarchies, because at that point you already have the physical address. You'd better do the TLB translation before the second level, for example. Okay, see backup slides for more. Let me now quickly go over a modern virtual memory system in Intel Skylake, and then we're going to transition to the epilogue part. So this is address translation has evolved a lot. So this is simple address translation in earlier systems. You have an L1 data, an L1 instruction TLB, L1 data cache, which is not part of your translation system, but usually you do it concurrently with the L1 data cache, as we discussed. And then there's a software page table workload like MIPS. Modern address translation is much more complicated. Modern MMU, you can think of this as MMU. You have L1, L2 ITLBs, L1 ITLB, L2, L1 data TLB, L2 TLB, page table Walker hardware, page table Walker cache to cache the middle levels of the page tables, multi-level page table. So there's a lot that goes on. And then there's also clearly the cache. So a memory management unit, we discussed it. It's responsible. It's the hardware that's responsible for resolving address translation requests. It's 1 MMU per core, usually. MMU has 3 key components, TLBs. We know what TLBs are. Page table vault caches. They essentially offer fast access to the intermediate levels of a multi-level page table. So TLBs cache PTEs, not the intermediate parts of the page tables, but page table vault caches cache intermediate mappings at the hierarchy, page table hierarchy. This is to aid the translation TLB misses essentially. And then hardware page table walker that sequentially does the page table walk that accesses the different levels of the page table to fetch the required PTE. And this is all in hardware. So now we can see that there's a big hardware over here. Okay, let's take a look at this MMU. Let's tear it apart in an Intel Skylake system, which is reasonably new. L1 data TLB, essentially, even this is complicated. Basically, they have 3 TLBs, each for different page sizes, 4 kilobyte, 2 megabyte, 1 gigabyte. And you can see the entries over here. There's only 4 entry 1 gigabyte TLB and fully associative. But this, you can address 4 gigabytes of memory with this. That's why it's 4 entry. 2 megabytes, 32 entries, you can address only 64 megabytes, right? With all of those. The 64 entries, you can address only 256 kilobytes, I guess, in this case. That's too bad. So this TLB is actually quite powerful. Even though it has fewer entries, it's very powerful because it really spans a 4 gigabyte portion of the physical memory. Okay, virtual memory, I should say, but also physical memory. I mean, if you think about it from that perspective, right? And virtual to physical mappings are inserted into the corresponding TLB after a TLB miss, clearly. And during a translation request, all 3 L1 TLBs are looked up in parallel. So now you can see that it's complicated. And having multiple page sizes clearly complicates the picture. And Intel folks did not design a single TLB with different page sizes because they thought it was easier to design 3 TLBs with different page sizes. And you can imagine, this is a cartoonish picture. You need to basically index these TLBs with different parts of the virtual address and do the tag match, etc. And then decide which one you hit on. Okay, so there's an L2 unified instruction and data TLB. Essentially, L2 unified TLB cache translation for both instruction and data. It's still private per individual core. And there are 2 separate L2 TLB structures now. One for 4 kilobyte and 2 megabyte pages, and one for 1 gigabyte pages. And you can see that these are bigger. But again, they decided to consolidate 4 kilobyte and 2 megabyte together. So the design of the TLB is a little bit more complicated for this one. Okay, but these are bigger, as you can see, and you can see the penalties. Of course, the question is, how can you support both 4 kilobyte and 2 megabyte pages using a single structure? There's not enough detail on this, but you can imagine, we discussed this actually when we talked about associativity in time. You basically index the TLB once using a 4 kilobyte index. And then if you miss, you index the TLB again. Okay, that's the idea basically. There are 2 steps basically. In time, you index the TLB assuming different page sizes. Okay. If you hit in the first step, that's good. Then it's a 4 kilobyte page. If you miss in the first step and hit in the second step, then it's a 2 megabyte page. If you miss in both, then you need to do the page table walk. The general algorithm is to recalculate the index and probe the TLB for all remaining page sizes. And we've seen this in associativity in time. If you remember the cache lectures, we said pseudo associativity. This is poor man's associative cache, if you will. We have associativity in space normally, but now we have associativity in time. We change the index and index into the cache again and again and again. And you can do it many, many times to get very high levels of associativity or support any number of page sizes. And this is the example basically. You first calculate the index for 4 kilobyte. If you miss, you calculate the index for 2 megabytes. Okay, so L2 TLB has n-step index recalculation. This is simple and practical. The downside is TLB hit latency is longer and varying. And now you have slower identification of L2 TLB miss as you need to basically probe all page sizes. So potentially you can optimize it by making the lookup parallel. Of course, this adds hardware cost. Or you can predict the page size, predict the probing order. And trade-offs are again similar to associativity in time versus space. Okay, let's talk about the hardware page walker components. As we said, TLB misses are handled in hardware. And this is an interesting component, complicated component. that walks the multi-level page table to avoid expensive context switches and software handling of TLB misses. It has two components. One is a state machine that is designed to be aware of the architecture's page table structure, and then registers that keep track of outstanding TLB misses. So I'm not going to go into the details of it, but you can imagine how the state machine walks the page table. Of course, we actually saw the slide earlier. This avoids the need for a context switch on a TLB miss. It also has the ability to overlap TLB misses with useful computation, as we discussed. It supports concurrent TLB misses, because in hardware, you can support many concurrent misses. But of course, there's a downside: hardware area and power overheads. And now the software cannot change the page table organization and properties, if you will. It's etched into the hardware. Okay, so how do you do this walk? I'm not going to go through this in detail, but you start with CR3 register and then concatenate CR3 with the virtual address, and then you essentially do the walk of the multi-level page table that we discussed earlier. So it takes time, basically. Okay, but of course, there's benefit to it. That's why it's implemented in real processors. It allows overlapping of many TLB misses with useful computation. So if you do the software TLB mishandling, you need to context switch to a TLB mishandler, and then you do a load B. You cannot handle this TLB hit because you have a context switch, right? Hardware page table walk, TLB miss. Concurrently, you can handle other TLB hits, so you can do out-of-order execution, and you can get the full benefits of out-of-order execution, etc. Right? So you save a lot of cycles actually with hardware TLB mishandling. It's also called a page table walk, basically. Okay, finally, to aid this hardware page table walk, there are page walk caches. As we discussed, it's different from the TLBs because TLBs cache the page table entries, the leaf nodes in the last level page table. Page walk caches cache stuff, going back to this picture, from essentially all of these other levels, not the real page table that you're looking for. Why? Basically, you want to speed up the hardware page table walk. That's the idea. I already said all of this, actually. These are low latency caches that provide faster access to the page table levels so that the page table walker does not have to access memory or the cache hierarchy for every page table walk. It can just access these page walk caches, okay? And that's the Intel Skylake MMU for you, basically, in a nutshell, very quickly. And actually, there are other virtual memory designs. This is Apple A14 over here, based on some reverse engineering, etc. But you can see that L1 TLB and L2 TLB are larger in Apple A14, and also the page size, the default page size, is actually larger. I'm not going to go through the details of it, but you can enjoy the slide on your own. Okay, so we're at the end of virtual memory. So to summarize, virtual memory has a lot of benefits. It gives the illusion of infinite capacity. And we already discussed everything, so I'm not going to go through all of this again. This is a summary of everything we discussed. But it provides you the illusion of infinite capacity. It also provides you protection. That's very important. And there are a lot of issues that you need to solve along the way. And those issues all exist in real systems, and they're solved in some way. But there's more, which we're not going to talk about. How do you handle virtualized systems? Pose the problem. I'm going to flash a slide related to this. You may have virtual machines and hypervisors running programs, orchestrating systems. Now you have another virtualization layer. And that actually increases the number of virtual memory translations that you need to do. And existing systems provide support for that, called nested page walks, for example. I'm not going to talk about that, nested TLBs. There are alternative page table structures that we did not talk about. Inverted page tables, we briefly mentioned when you want to actually, the operating system may store the reverse mappings from physical pages to virtual pages to figure out what to replace. Some systems actually have inverted page tables to begin with, probably a bad idea, but there are trade-offs associated with it because inverted page tables are actually quite compact. In terms of storage size, these are small. Hashed page tables can enable fast access to the page tables. Actually, this may be a good idea to revisit in many systems, which we did not talk about. Basically, we just directly indexed. We didn't really do sophisticated hashing to the virtual address. And there's more that we don't have time to cover. But I will show you the one picture over here, which is the virtualized system. You may have a virtual machine, for example, like VMware. You may have a guest OS running on a host OS, running on the physical CPU. And this virtualized environment needs to have an additional level of address translation from the guest OS virtual address to the host OS virtual address. And then host OS virtual address needs to be translated to the host OS, the CPU physical address, essentially. And that requires another level of layer of translation, if you will. And this leads to a lot more memory accesses, basically. I'm not going to go over it, but it's a lot of memory accesses. And existing hardware, x86 hardware for sure, provides support for directly translating from the guest virtual address to the host physical address, while trying to avoid as much as possible this indirection level. So that's a direct support for virtualized systems. Okay, so let me conclude with this parting thoughts, the virtual memory part, and then we're going to have an epilogue for those who wish to stay in the rest of the lecture. But virtual memory is actually very important because it's one of the most successful examples of multiple things. Architectural support for programmers, how to partition work between hardware and software. So it's really hardware-software cooperation, which is similar to what I said over here. And it's a very successful example of the programmer-architect trade-off. It basically makes programmers' life super easy, architects' life, both system architect and micro-architects' life harder, as we have seen. But it is one of the most successful examples. But going forward, how does it scale into the future? It's not doing very well, in my opinion. And there are a lot of papers that are written on it. I'm going to show you some pictures of it also. But basically, we have increasing huge physical memory sizes, both local and remote. And 256 terabytes are starting to sound small for our memory sizes, basically, because data is huge. We have hybrid physical memory systems, DRAM, NVMe, SSDs, and we want to increasingly manage everything using a single memory abstraction. There are many accelerators in the system addressing physical memory. They want to be part of the virtual memory. And there are virtualized systems, like I showed you earlier, hard hypervisors, software virtualization, local and remote memories. So how does it scale into the future? So the management is actually quite complex overall. So it's not going to scale very well. So there's one question. In case of hashing, will the synonym and homonym problems be reduced? Not necessarily. That's a very good question, but not necessarily. Basically, you still have a virtual address and you still have a physical address. It's just a way of determining the mapping. Okay, so if you want to learn more about rethinking virtual memory, we do a lot of that in my research group, actually. And this is one of the papers that we have written last year that rethinks virtual memory from different perspectives. You can also watch a lecture related to it. This tries to solve the rigid page table structure problems, translation overheads, which we have discussed many times, and heterogeneous memory management. But if you're interested, we're not going to cover it. You can take the future lectures or also read the paper. And there's a lot more in virtual memory. Like if you want to know more about the synonym and homonym problems, we cover that in other lectures, but we don't have time to cover it in this lecture. But you can also watch lectures. As you can see, there are multiple solutions to the problem. Okay, there are more lectures on virtual memory that I'm not going to go over right now. But hopefully this gave you a reasonably comprehensive overview of issues in virtual memory, which I think is critical to get exposed to as early as possible in your career, because it is a lot of cool ideas. It is a lot of complexity at the end, but it's one of those things that has been successful despite the complexity, heavy complexity, because it makes programmers' life easier.